Okay, so we're trying to find the volume underneath this graph of f as a function of both x and y. And so in number one, the idea is that we're fixing a certain x coordinate and we're going to go along the y direction. And right along this particular x coordinate, x is constant, and we can just figure out what is the total area above this slice. So our function, what was our function? Our function was x squared plus y squared plus 1. X is acting like a constant here, and we need to add up all of these sort of vertical slivers of area that sit above every point along this line segment. And the y coordinates that show up are from, let's see, this lowest one down here, which is going to be 0, up to this highest y coordinate, which is, let's see, how big is this rectangle? It goes up to 1 in the y direction, so 1. So this is going to be the area above this slice. Of course, this actually all depends on x. So this is a function of x, as I said down here. So we can call this a of x. And this integral is, y is the variable in this integral, and x is acting like a constant in this integral. So when we do this integral, let's see, we get, the integral of x squared treating x like a constant and y like the variable. This is going to be x squared y. Okay. And then plus, treating y like the variable, the integral of y squared is 1/3 y cubed. And then the integral of 1, treating y like the variable, is y. And then we need to plug in our bounds. There's nothing about the notation that tells us which variable these bounds are for, but remember, these are y values. So if we want to, we could sort of amend our notation by explicitly writing down what variable these bounds are for. Okay, so then when we plug everything in, we get x squared times 1, so that's x squared, plus 1/3 times 1 cubed, that's 1/3, plus 1, minus, and then plug in our zeros, and we get nothing but 0 when we plug in our y values. Okay, so this area function, that is the area above the slice at position x, that area is x squared plus 4/3, it looks like. Okay. All right, so what is the thickness of this slice? Well, this is an area. If we want to sort of thicken it up a little bit in the x direction so that we get a volume, well, the slice is infinitely thin in the x direction, so the thickness of that slice is just dx. All right, so the volume above the slice, well, that's going to be the area of that slice times the thickness of that slice, which is dx. So the volume is, we could call this dv, I guess. The volume is this area the area a of x times dx. So to add up all the bits of volume to get the total volume, well, we just need to add up all the bits of volume, integrate dv. So we're going to integrate our area function, which was, what was it? X squared plus 4/3. dx. And then we need to write down what x coordinates give us little slices of volume, So the most leftward slice is over here, the most rightward slice is over there, and those bounds, if we sort of look up at the top, those bounds were from -1 to 1. So we can integrate this from -1 to 1. And this is a single variable integral, so this is sort of in the usual way, 1/3 x cubed plus 4/3 x. Evaluate this from -1 to 1. So this is 1/3 plus 4/3 minus, and then plug in your -1, minus 1/3, minus 4/3. So this is going to give us, let's see, 5/3 and then another 5/3 in the brackets, so that's going to be 10/3 altogether. All right. Well, taking a step back, you can see what happened here is so actually let me rewrite this. So this integral of our volume was the integral from -1 to 1 of our area function dx. But that area function itself was an integral. So the area function was the integral from 0 to 1 of x squared plus y squared plus 1 dy. And then the outside integral is dx. So, you know, in the single variable context, when we looked at integrals, like integral of f of x dx, their geometric interpretation of that was the area under a graph. So if we integrate a function of two variables, we still get the amount of stuff under a graph, but we get the volume under the graph. And of course, that's because in the two variable context, a graph has volume below it, not area below it, right? So the upshot of all of this is when you have a function of multiple variables, if you want to integrate it, there's an integral sort of in each direction. And if you want a number, if you want to compute a number for a result, like the volume under the graph, you end up doing two integrals, not just once. So what we're going to have to understand to really lock down what's going on here is we're going to have to understand this phenomenon of multiple integrals. Okay, so that's what we're going to be studying.